Further ado, I would request Asher to please start today's session.
Okay, thank you for the invite, and I'm excited to be here. As you guys can see, I have a virtual reality headset on, so I'm going to set that up for you guys and share my screen. Make sure you guys can see inside the virtual world that I see. So let's do this, let's do that, let's do screen share. Screen. All right. Is my screen share on, Koyani?
Sorry, yes, it is.
It is? Okay, it's working. It's in my virtual room.
All
right, I'm going to turn my my real self off so I can actually I can leave my real self on. That's fine. Okay, so I think it'll stable connection. All right, audio is good and everything. Let's get
Yes,
started.
everything is fine.
All right, so let me grab. So as you guys can see, I'm in a virtual room right now, and this is this. Oh, got my camera here. Stable camera. Okay, so my talk will be on exploring protein data bank resources. Basically, virtual reality as a resource for in-silico ligand receptor analysis. So because this is all in a virtual reality space, it should be pretty interactive. So the outline of the talk will be as follows. So what is virtual reality? Why is virtual reality useful? We'll talk about the protein data bank. We'll talk about ligand receptor interaction, molecular dynamics as we heard about in yesterday's talk, and then we'll look at the COVID spike protein in VR. So virtual reality, what is this? VR, abbreviated as virtual reality, is a simulated experience that can be similar or completely different from the real world. In the case of this room, this is much different than the real world. You can't interact with small atomic particles in the real world in 3D space. Modern VR began in 2012 when the company Oculus, which is actually now owned by Facebook, released the Oculus Rift. VR's biggest application is definitely still video games, but its potential in education and research is a growing field. This is becoming a huge field in VR research. And then in 2015, the San Diego, California-based company Nanome was launched, okay, which is the VR platform that we're in today. So Nanome is a virtual reality software that is used for drug discovery, molecular modeling, rational protein design, and most importantly, education. And this is a program that I am really in love with. I've fallen in love with. So the protein data bank, the PDB, is a resource containing an archive of information about the 3D shape of proteins and nucleic acids. Every structure has a unique code consisting of numbers, letters. For example, one of the proteins we'll explore today has the code 5L4Q. It's the structure of adapter protein 2 associated kinase, abbreviated as AAK1, in complex with an inhibitor of the protein called LKB1. Inhibitors of AAK1 have been suggested as possible candidates of the treatment of COVID-19, as this interrupts the passage of viruses into cells. So in doing this live demonstration, I'm going to pull up my web browser and kind of just quickly show you guys the protein data bank. Let's see, web browser, and I'll put this here. So here's our web browser inside of virtual reality. If we go to the RCSB, the protein data bank, this is the server that we can get all of our PDB files off of, as we talked a little bit about in this seminar. So this is where we get all of our resources for files, and we can directly upload them to these virtual rooms to interact with them. Oops, sorry, there it is. Here's the PDB, I forgot to share that. So the PDB is this resource for protein data bank files that we can upload into virtual space and interact with them, as we'll talk about in a minute or so. Exit that. Okay. So ligand receptor interaction. This looks at how a ligand or drug interacts with a biological target in 3 dimensions. There are certain intermolecular forces of attraction that hold ligands bound to certain areas of receptors. And these are things like hydrogen bonding and electrostatic forces like pi-pi stacking and these types of interactions. So let's actually look at a protein in virtual reality. So I'm going to pull this off. And then you guys can see I have an entry list over here with all of my working files in VR. So the protein that we're looking at today is going to be AAK1, which is right here. So I can take this protein and I can make it a little bit bigger so we can see it a little better. And as you guys probably have talked about and already know, in biochemistry, you learn about certain protein shapes that proteins make. In red, these are called alpha helices, okay, in red. In yellow, these are called beta sheets or beta pleated sheets, okay. And then these little coils are just called loops. Basically, they are loops that connect either a beta sheet to a beta sheet, or in this case right here, a beta sheet to an alpha helix. Okay, and then if we go quickly back to the PowerPoint slide. Okay, the nitrogen atoms of the pyropyridine moiety form hydrogen bonds to AsP127, aspartic acid 127, and cysteine 129. So let's actually look at that in VR, how that looks. Okay, so if we go back to our entry sheet, we can actually highlight those certain amino acids on this PDB file. If we go to this little option here, okay, and then we go to open hierarchy. Let's go back. If we go to this one, open hierarchy, we select our hierarchy. These are all the amino acids in the protein. So as you can see, as I highlight over them, certain regions on the protein get highlighted. So the amino acids that I'm looking for to show the hydrogen bonds are aspartic acid 127 and cysteine 129. So if I go to my entry list over here, if I scroll down to 127, 23, 24, 25, 26, 27. Okay, I want 127. I also want 129. And then I also want this one down here, which is lysine 74. And then lysine 70. Whoops. Lysine 74. There it is. Oops. Okay, so to actually, as you can see, if I look at my protein now, those regions that I selected or highlighted, what I want to do now is show those regions in VR. So if I go to my display menu, I can display these as sticks, okay, which is really cool. So I can show those bonds to actually show those amino acid residues in VR, how they hydrogen bond. I'll do the following. Let's close this hierarchy menu. And let's go to measure. Okay. So one of the hydrogen bonds was 127 and 129. Let's actually do one more thing. Let's label those. If I do that, now you guys can see all of my residues are labeled. 129, 127, 74 makes it much easier to interact with. Delete that. Okay, so 129. Let's make this a little bit bigger. Okay, 129, there's a hydrogen bond here. 129. Oops, that's weird. $129. Okay, that's sitting at a distance of 1.76 angstroms. A hydrogen bond will sit around 2 angstroms as an atomic distance. Okay, 129, 127, that will be this hydrogen to this oxygen, which is at a distance of 2.11 angstroms, and then lysine 74, which will be this, well, I guess it'd be this atom to this atom, sitting at 2.16 angstroms. So as we can see, we can really start to use virtual reality to help us look at proteins in three-dimensional space, and that's really useful in a way. Okay, so we basically here what we looked at is this ligand, which is an inhibitor of this protein. I believe this protein normally binds ATP. So ATP would come into this active site right here. And usually there's a triad of 3 amino acids that'll cleave it into a few different pieces using organic chemistry. Okay, so we looked at that. So we looked at all 3 of those hydrogen bonds in a ligand receptor interaction. The next thing to look at is molecular dynamics in VR. We actually had a nice MD simulation workshop yesterday on this, so I won't bore you too much with MD simulation talk. Computer simulated method for analyzing the physical movement of atoms and molecules. Kalyani could probably correct me on this. The simulation set to run for about 100 nanoseconds. We can watch a trajectory of the simulation to understand how the ligand and receptor interact with respect to time. And that's really the major difference between an MD simulation and a still frame docking as we have here. This docking is just simply how the ligand looks bound in the receptor in sort of a frozen conformation. There's not a respect to time here because this is not a trajectory that's moving. And that's the difference between an MD trajectory. An MD trajectory has this with respect to time, as we'll look at. In the case of AAK1, we can actually observe how the hydrogen bond distances change with respect to time. And that's what we'll actually look at here. So let's play our trajectory. Close that. And we will go to our advanced menu to play our simulation. And we also need this one. I'm going to set this to 1x at first because the simulation does move very quickly. And then we can play it. Okay, so as we can see, what's going on if we look at the simulation is that if we notice the different hydrogen bonds that I've highlighted are changing distances, because as we said, this was an MD simulation, so it's looking at how this molecule is moving within the binding site of the enzyme in this case with respect to time. So if we look at, for example, let's look at cysteine 129 first. So cysteine 129 was one of the hydrogen bonds that we said existed. It's hovering around an atomic distance of about 1.8 angstroms if you took an average. So we can see that this is a nice hydrogen bond that interacts with cysteine 129. If we look at aspartic acid 127, we can see the bond range in the simulation is staying around 2 angstroms. Okay. Now, this one that's reported in the crystal structure paper actually changes a lot in the simulation, way more than I would like to see it change. I think what's going on is this ring so this ring right here, the nitrogen, is flipping back and forth, and that changes the distance of the hydrogen bond by quite a bit. Sometimes we see it at 3 angstroms, sometimes you see it at 5, sometimes you see it at 2. This one's a little bit, I'd say, weaker looking at the simulation. It's not as good of a hydrogen bond because this whole ring can flip. There's a carbon-carbon single bond right here, which means that this ring can flip both ways. It doesn't lock it into one conformation, so to speak. Okay, let's pause that simulation. We can get to some other stuff. And we can take that away for now. Let's delete all these. think we can actually just do that. Okay, we'll delete those that way. And the last thing I want to look at, okay, is COVID spike protein and mutations. So we're going to take a look at one of the COVID spike proteins, PDB ID 7TN8. This is a cryo-EM structure of the spike glycoprotein. And then we're actually going to use VR to look at the Delta variant, which has mutations in the gene encoding for the SARS-CoV-2 spike protein, causing the substitutions D614G, T478K, P681R, and L452R. And that would actually be nice to look at. Okay, so we can grab our spike protein. These spike protein mutations. So we have 614 highlighted over here. 614. The next one we'll go to is 681. So 681. Let's pull this a little closer. 684, 83, 82, 81. Oops. 674, I think it's this one. 84. 74, 75. Yeah, okay, so it's the P. Okay, and then we're looking for 478. 478, 74, 75, so 677, 78. And then we're looking for 452, 54, 53, 52. Okay, so now what we can do is we can actually bring these amino acids to life and make them visible. Go to display. We're gonna turn those residues on, and then we will also stick. There they are. They're a little hard to see. Let's make them a little bit bigger. There should be 4 of them. 1, 2, 3. There should be 4. There should be 4. Let's make this a little bit bigger. I see 2 of them highlighted. We've seen 452, 3, and then 478. There should be. Oh, there they are. Sometimes they're hard to find on these big receptors. There are the other 2. Okay, so you guys can see these. Let's start at aspartic acid 614. Okay, so this is pretty interesting. So within the spike protein, to make the delta variant, we have 4 mutations. So D614G. Okay, so what we want to do is mutate that. So if we select that residue, and then if we go to, delete out of this, it's probably under modify. There's mutate. Okay, so we have our mutate menu now, and we can mutate those amino acids. So as we can see, I've got a menu in front of me that allows me to change the amino acid. So D614G, aspartic acid 614, we're going to change to a glycine. So if I do that, it'll change to a glycine. That's one of the amino acid mutations. The next one, let's do the 681 because that's closer by. There it is. 681 is a proline. So I'm going to select my proline. I'm going to change it from a proline to it looks like an arginine. Okay, so there's that mutation. And then we have 2 more. We've got 478. 470. There it is, threonine. So 478, I'm going to highlight that, and I'm going to change it to glycine. So I think it's quite interesting in molecular biology that we can just have these 4 amino acid mutations. We can look at them in VR to understand what happens in the spike protein to cause these mutations that lead to, in these cases, probably more transmissible forms of COVID. And with that being said, that is the end of my talk. So the people that really helped make this happen is, of